Welcome to today's session. In the previous session, we have observed frequency modulation and how can we represent frequency modulation by using waveforms and equations. In today's sessions, we will see some of the things about frequency modulation. As we have seen in amplitude modulation, the modulation index, which will give the depth of modulation. Same thing coming to FM also, will be having our modulation index. Here we will represent it the modulation index with MF, where coming to the definition of modulation index, it is defined as the frequency deviation to the modulating frequency. In the previous session, I have given what is meant by frequency deviation, which is represented by del omega. So, here modulation index of frequency modulation is depends upon the ratio of frequency deviation to the modulating frequency. So, del omega by omega m we can write, or del f by fm we can represent. Then coming to the modulation index, whether it is greater than 1 or less than 1, depending upon the modulation index, it will this FM is divided into two types. That is, one is narrow band FM and wide band FM. That's what here we are representing in the slide. Modulation index of FM decides the bandwidth of FM wave. So if it is less than 1, we will call it as narrow band FM. So as the name indicates narrow band, so the bandwidth will be very, very less. If modulation index is greater than 1, then it is known as wideband FM. As the name indicates, the bandwidth will be large. So that's why it will decide the bandwidth of FM wave. Depending upon the bandwidth, the number of sidebands of FM wave can be decided. So deviation ratio, we all know that maximum deviation to the maximum modulating frequency. If we want our percentage of frequency modulation, we need to go for into 100. Then mathematical representation of FM already we have seen in the previous sessions. Today, in this session, we will see the types of frequency modulation. As I told before, depending upon the modulation index, either MF is greater than 1 or less than 1, narrowband FM and wideband FM, these are the types of frequency modulation. So if it is narrowband FM, the modulation index will be small. If it is wideband FM, the modulation index will be large. Here we are representing some of the differences between narrowband FM and wideband FM. Here, if it is narrowband FM, as we are stating before, as I stated, it is slightly less than 1, and it is wideband FM modulation index will be greater than 1. And the maximum deviation in narrowband FM is up to 5 kHz, but in wideband FM it is 75 kHz. Why? Because it is wideband. And modulating frequency, usually in narrowband FM we will take it as 20 Hz to 3 kHz, but in wideband FM also we can increase that to 15 kHz, 20 Hz to 15 kHz. Modulation index will be greater than 1, and it here in wideband FM it is 5 to 2500. And bandwidth, for narrowband FM bandwidth is 2 FM, but for wideband FM it is 2 into del F plus FM into FM, del omega plus omega m we can represent in terms of angular frequency. Coming to the applications of narrowband FM and wideband FM, narrowband FM mostly we will be using in mobile communications and walkie-talkies, police wireless, ambulance. For short range communication, we can go for narrowband FM. Wideband FM, usually our broadcasting with high quality of music transmission, TV, for music alone, we'll be using our wideband FM. Now we will see the time domain and frequency domain waveforms of this FM. So this particular waveform already we observed it is our time domain frequency modulation output waveform, modulated waveform. That is where it is the frequency is varying with respect to input message signal. If it is positive half cycle, more variation will be there. If it is negative half cycle, less variation will be there. Coming to frequency domain representation, that is in terms of frequency spectrum, we can represent in this way Fc, as there will be sidebands. By Bessel functions, we will be getting our sidebands like Fc plus Fm, Fc plus 2 Fm, Fc plus 3 Fm, and this is Fc minus Fm, Fc minus 2 Fm, like that. Upper sidebands and lower sidebands will be there. So this is the time domain and frequency domain representation of frequency modulation. Coming to the next topic, that is, we need here pre-emphasis and de-emphasis. Actually, these pre-emphasis, de-emphasis circuits are used only in frequency modulation while transmission and receiving of our information. At the transmission side, we will be using pre-emphasis. At the receiving side, we will be using our de-emphasis. Actually, for what purpose we will go for pre-emphasis means, at some higher modulating frequencies, we observed input signal up to 15 kilohertz also we can take. So at that particular higher modulating frequencies, the noise effect will be more. To reduce this particular noise, we will be using our pre-emphasis. How can we reduce this noise means by increasing the value of modulation index for higher modulating frequencies. For this purpose, we are going for frequency pre-emphasis. This can be done. How can we increase this modulation index means by increasing the deviation. Why? Because already we observed our MF equals to formula del omega by omega m. So as it is directly proportional to our frequency deviation, by varying this frequency deviation, by increasing this one, we can increase the modulation index so that we can reduce the noise, especially for the amplitude of modulating signals at higher frequencies, which will increase the so that it will increases the amplitude of modulating signal at higher frequencies, so that the noise will be reduced. So the actual definition of pre-emphasis is, here we are artificially boosting up of higher audio modulating frequencies in accordance with pre-arranged response curve, that is known as pre-emphasis. The circuit diagram of pre-emphasis is shown here. By using one transistor we can use, and it is a combination of capacitor and resistor. It is a combination of capacitor and resistor where we can take our output across the resistor. So as we are taking our output across the resistor, it is nothing but simple high pass filter we can say. So pre-emphasis is also known as high pass filter. Coming to de-emphasis, this is the curve of pre-emphasis curve. It is increasing. As pre-emphasis is used at the transmission side, so this is the simple block diagram you can see. Then coming to de-emphasis circuit is used at the FM receiver side, where pre-emphasis is also known as high pass filter depending upon the circuit. Here, as we are artificially boosting up the higher modulating frequencies at the transmission side, we should nullify it at the receiving side. For that purpose, we are using de-emphasis, where whatever the artificial boosting have higher modulating frequencies will be nullified by the process known as de-emphasis. We will be using after demodulation process, so that after FM demodulator we will be using this process. This is our de-emphasis circuit, which is a combination of resistor and as well as capacitor. The output is taken across the capacitor. By this we can observe that it is also known as low pass filter, where low pass filter is a filter which will consist of two components, resistor and capacitor, where the output is taken across the capacitor. So this is the de-emphasis circuit. And this is the curve of de-emphasis where it will decreases. That means whatever the increasing we are doing at the transmission side will be nullified at the receiving side, known as de-emphasis. And here some of the comparisons we have given in pre-emphasis and de-emphasis. The circuit of pre-emphasis is nothing but high pass filter, de-emphasis is nothing but low pass filter. Circuit diagram we are showing here, waveforms we are showing here. Coming to time constant, we should maintain 50 microseconds here. What we are doing here means boosting up of higher frequencies, amplitude of higher frequencies, and we are nullifying in de-emphasis. Actually, pre-emphasis is used in FM transmitters and de-emphasis is used in FM receiver after demodulation process. So thank you for listening. Some more we will be seeing in our next sessions. Thank you.